Hello everyone, I welcome you all in lecture 5 of module 2 AFD, SFD and BMD in beams under mechanics of solids. So we will go through one more numerical related to shear force diagram and bending moment diagram. The statement of the numerical is something as shown. Analyze the simply supported beam as shown in the figure and hence draw SFD and BMD. And in addition to that, the statement of the numerical is also find the position and magnitude of maximum bending moment. So that we have done in a few numerical earlier, and locate the point of contraflexure. So this is addition. So as usual, it is a simply supported beam hanging over one of the supports, and it is subjected to UDL 22 kN per meter or 5 meter distance, and then 58 kN point load at free end, and support A is hinge support and support B is roller support. So we'll go through drawing the free body diagram of this beam. It will be something as shown in figure 10b. So you have two reactions at hinge support. So one is the horizontal reaction HA and vertical reaction VA, that is to be calculated, and the vertical reaction at B support is required to be calculated. So we will be applying equations of equilibrium as usual. If we apply summation of x equal to 0, HA is the only reaction, there is no inclined or horizontal force, so HA is 0. And if we apply summation Fy equal to 0, you have two vertical reactions VA and VB. So VA plus VB, and then whatever forces are acting on the beam, due to UDL, the total force will be 22 kN per meter multiplied with 5 meter distance on which it is acting. So 22 into 5, that will be negative, and 58 kN downward point load. So that will be again minus 15. That total must be equal to 0. So actually equation is VA plus VB minus 22 into 5 minus 58 must be equal to 0. So if we calculate it, VA plus VB is equal to 168 total. So if we go further and apply summation of moments of all the forces about a particular point is equal to 0. So if we consider about support A, then the equation will become something like this. Due to uniformly distributed load 22 acting over 5 meter, so that moment will become 22 into 5, and its centroid from A will be 2.5 meter. So that moment becomes 22 into 5 into 2.5, and that is clockwise, hence written to be positive. And due to 58 kN point load acting at C, so that distance is 7.5 meter from support A. So moment due to that point load will be 58 multiplied by 7.5, and that is also clockwise. So 58 into 7.5, and due to reaction at B, that will be VB into 5, that is distance from support A up to support B where that reaction is, and then that is anti-clockwise, so it is written as negative. So minus VB into 5, that is moment of that reaction. That total sum must be equal to 0. Hence, if we calculate with this what is the reaction at support B, that VB gives us 142 kN with this equation, and if we substitute this VB as 142 kN in earlier equation summation Fy equal to 0, then we get VA as 168 is total VA plus VB, and with that if we substitute VB is equal to 142 kN, then VA will be 168 minus 142. So that will be 26 kN total reaction at support A. Now in between support A and support B, we have a uniformly distributed load, so we need to consider one section at in between A to B. Okay, and beyond B up to C, we have the reaction at A, UDL acting from A to B, as well as reaction at B. So we need one more section in between B to C. But in this numerical, instead of going from left at a particular section, section 2 to will be considering forces acting on right part of that particular section. So we'll go through the calculations of shear forces. So considering section 1-1 at x1 distance from support A, in between support A up to support B. So over here, considering section 1-1 in between points A and B at distance x1 from A with origin as A, and if it is applicable from A up to B, so x1 becomes 0 at A and 5 meter at B. So limits for the equation are from 0 to 5 meter. So if we consider the forces acting at the left part of section 1-1, then the equation will become SF11 equal to, at the left we have this 26 kilonewton reaction and it is upward. So it is plus 26, and then downward UDL is there. So 22, now if we are considering section 1-1 and up to left of section 1-1, 22 kilonewton per meter UDL will be acting over length x1. So that will become minus 22 into x1, that is total force due to UDL. So now if we put the limits at x1 equal to 0, that is at point A, then this the second term becomes 0, and that gives SF at A as 26 kilonewton. And if we put the limit x1 is equal to 5 meter, at B shear force is minus 84 kilonewton. So if we go through section 2-2 at x2, now what we are considering is section 2-2 is applicable from point B up to point C, and instead of considering left part of section 2-2, we will be considering what is acting on right part of that section. So now origin is C, the limits are from C to B, from C. So that becomes 0 to 2.5 from C up to B, and x2 is distance from C as origin. So if we write equation for this, then at the right part of section 2-2 we have only 58 kilonewton force, and that is downward. And in sign convention we have discussed that if we are considering left part of section, then the upward forces we will be considering positive and downward forces we will be considering negative. However, if we are considering right part of section and forces acting on right part of the section, then downward forces we will be considering as positive and upward forces we will be considering as negative. So this gives us SF22, and at right of section 2-2 we have only 58 kilonewton force. So that becomes plus 58, and with limits as x2 is equal to 2.5, that is at B, that value of shear force is 58 kilonewton, as well as at point C, that is free end. So at that position the value of shear force is 58 kilonewton. So once we calculated these different points at different points what the shear force is getting developed, then we can draw that shear force diagram. So it is as shown in figure 10C. So now if you go through equation 1-1 of this SF11, then x term is there and power of x is 1. So in between A up to B, the variation of shear force is inclined line. Okay. And at A it is plus 26 kilonewton shear force, and at B it is minus 84 kilonewton shear force. So it is drawn downward, and then it is connected with inclined straight line. And at B you have two different values. One with SM11 equation we have shear force as minus 84 kilonewton, and SF22 equation that gives SF as 58 kilonewton. So from minus 84 up to plus 58, that is the change in the shear force. So that is total sum of 142 kilonewton reaction at B. So this 84 plus 58 together will be 142. And at C it is point load 58 kilonewton. So the value of shear force just at left of C will be 58 kilonewton. So this gives us a shear force diagram for given numerical. So if we go further with calculations of bending moment, then at section 1-1 up to section 1-1, if we consider left part of it, okay, then on the left part of section 1-1 we have reaction at A as well as UDL up to section 1-1 from support A. So we'll be having bending moment due to reaction as 26 into x1, and that will be clockwise, so it is written as plus, and due to UDL 22 into x1 is the total force due to UDL, and that will be at centroid, so it will be at x1 divided by 2 from support A. So from section 1-1 it becomes again x1 divided by 2. So total bending moment due to UDL become 22 into x1 divided by 2. So it is written as 22 x1 square divided by 2. So if we now put the limits at x1 equal to 0, that is point A, support point, at that point bending moment is 0, and at x1 is equal to 5 meter, that is at B the bending moment value is minus 145 kilonewton meter. And if we go further at section 2-2, and again if we are considering the forces acting on right part of it with origin as C and from C to B, so limits are from 0 to 2.5 meter. So if we consider that, then we get bending moment 2-2 from right part of it as 58 is the force and x2 is the distance, so 58 into x2. And this is hugging type of bending moment from B to C, because C is free end and B is simple support. So C point will be getting deflected down, and it will be creating the hugging type of bending moment. So it is written as minus 58 into x2. So at C, at point free end, x2 is equal to 0. So that gives bending moment as a 0 kilonewton meter, and at point B that x2 is 2.5 meter. So again that gives us bending moment at B as minus 145 kilonewton meter. Then how to draw this diagram? Try to understand. At point A bending moment is 0. At point B bending moment is minus 145 kilonewton meter with bending moment 1 equation. Similarly at same point with bending moment 2 equation, value of bending moment at point B is minus 145 kilonewton meter. So it is not like this, that at A it is 0, at C it is 0, and directly at B it is minus 145. It is not like that. So what is required further is, if you go through this shear force diagram which we have drawn earlier, then one of the point in between A to B the shear force is 0. And we have discussed that dm by dx is 0, means shear force is 0, and dm by dx is 0, then bending moment at that point will be the maximum. So what we will do now is the shear force 1-1 equation, whatsoever we have written, that we will be equating it to 0, so that we can calculate the position where bending moment is maximum. So if we observe this shear force diagram drawn in figure this 10C, shear force is 0 in between points A and B, where bending moment must be maximum. Hence, equating the equation of SF11 to 0. So, if we equate it to 0, we will calculate x1 distance. So, that x1 distance is calculated as 1.182 meter. Then, if we substitute this x value 1.182 meter from A in maximum bending moment using equation bending moment 1-1, if we put it in that equation, maximum bending moment is 15.364 kilonewton meter, and that is positive, or you can say it is sagging type of deflection. So try to understand, even though we calculated 3 different points, and at 3 different points what is value of bending moment, and directly if we draw that bending moment diagram, it cannot be correct one, because at A it is 0, at B it is minus 145, and at C it is again 0. So you may be under impression that everywhere it is minus bending moment or hugging type of bending moment, but in between A up to distance that 1.182 meter, that is sagging bending moment. Okay, and at point in between A to B at x is equal to 1.182 meter distance, the bending moment value is 15.364 meter, which is maximum sagging bending moment. So Now if we draw that diagram, it will be all right. So similarly, as bending moment from A up to 1.182 meter is sagging, and from C to B, if we consider, then it is hogging. Hence, bending moment somewhere in between A to B, beyond position of maximum positive bending moment, is changing its nature. So it is changing from sagging bending moment to hogging bending moment in between A to B somewhere, which is called as point of contraflexure. So that point is required to be calculated. So again, if we equate that bending moment 1 equation to 0, then we will be getting that value. So what is written is bending moment 1 was 26 into x1 minus 22 x1 square divided by 2. And now if we equate it to 0, then we will be getting that equation, we will be getting x1 distance, and that x is 2.364 meter from point A, and nature of bending moment is changing from sagging to hogging, which is point of contraflexure. So if we draw now that bending moment diagram, that will be as shown in this figure 10D. Okay, so here what we have calculated initially, that bending moment at A is 0, bending moment at B is 145 kilonewton meter, and that was negative. So that is hogging type of bending moment. And at C, the value of bending moment is again 0. But then we calculated at in between A to B, somewhere where shear force is 0, that position we calculated, and that was x is equal to 1.182 meter. And then we calculated the bending moment value at that point. So that value was 15.364 kilonewton meter, and that was positive. So that is sagging. And then in between this point up to point B, somewhere in between, the bending moment is changing its nature from sagging to hogging, because beyond this point at B, it is a negative bending moment. So then we equated that bending moment 1 equation to 0, and then we calculated the distance x, where the bending moment value is 0, or else what can be said that sagging bending moment is changing its nature to hogging bending moment, and that was x is equal to 2.364 meter from support A. So that point, as shown over here as P, is the point of contraflexure. So that was the complete numerical. It was asked to find the shear force diagram, then bending moment diagram, and then find position and magnitude of maximum bending moment. So sagging maximum bending moment is 15.364, and hogging maximum bending moment is 145 kilonewton meter. And also it was asked to find point of contraflexure. So that position we calculated by equating that equation to 0. Okay, so that you need to draw the bending moment diagram and find the position at different points where bending moment is either maximum or it is changing its nature. So we'll go through one more numerical. So a statement of the numerical is something like this. Analyze the simply supported beam as shown in the figure, that is 11A, and hence draw axial force diagram, shear force diagram, and bending moment diagram. Also find the position and magnitude of maximum bending moment and locate the point of contraflexure. So up till now, whatever numerical we have considered, in those numerical axial force diagram we have not calculated, or it was not asked. But here in this numerical, it is asked to find the AFD also, axial force diagram also. So that discussion we will do with this particular numerical. So the numerical is like this. The beam is simply supported. At A it is hinge support, at B it is roller support. BC is overhanging and C is free end, and it is subjected to uniformly distributed load from B to C. So that is 20 kilonewton per meter over 2.5 meter distance. And at point D, which is at 3 meter from support A, it is subjected to inclined load. So that is 120 kilonewton. So then its angle is 60 degree with x-axis or horizontal. Okay. So if we now go through free body diagram, that diagram will be something like this. Okay. So what is done over here is, of this 120 kilonewton inclined force, horizontal component of that is calculated, and that will be that 120 into cos of 60 degree. So that will be 60 kilonewton. And vertical component of that 120 kilonewton inclined force will be 120 into sin 60. So that is 103.9 kilonewton. That is vertical component of inclined 120 kilonewton force. And at support A, as it is hinge support, you will be having two reactions. One will be vertical and another will be horizontal. As well as at B, as it is roller support, there will be vertical reaction. So these reactions are required to be calculated initially. So using equation of equilibrium, applying summation fx equal to 0. So what the equation will be? You have HA as a reaction over here, HA plus now 120 into cos 60, that is horizontal component of this inclined force, that must be equal to 0. So that gives us HA as minus 60 kilonewton. Minus 60 means actually its direction is opposite to that force. So it is 60 kilonewton in negative x direction. That is what is drawn in the free body diagram. And then if we apply summation Fy equal to 0, then what equation we will be having is Va is one of the reaction, and then Vb is the another reaction at support B. So these two supports are assumed to be upward as positive, and then you will be having vertical component of this 120 kilonewton force, that is 103.9. It is by 120 into sin 60, and then this 20 UDL. So 20 into 2.5. It is acting on 2.5 meter. So 20 into 2.5 must be equal to 0. So that equation gives us Va plus Vb is equal to 120 sin 60 plus 20 into 2.5. So that is total force due to UDL. So that gives us 153.9. Okay. So if we go further by applying summation of movement of forces about support A, and if we equate it to 0, then we'll be having movement due to vertical component of this inclined force. Horizontal component of this inclined force will be passing through that support A itself. So you need not consider that moment, because moment of that will be 0 at A. And vertical component, if we consider, that is 120 sin 60. Okay, and its distance from support A is 3 meter. So that will be 103.9 or 120 into sin 60 into 3 meter. So that is clockwise, it is written as plus. And due to UDL, that will be 20 kilonewton per meter acting on 2.5 meter. So total force is 20 into 2.5. And its centroid will be at 2.5 divided by 2. So that is 1.25 from support B. So from support A, it will become 5 plus 1.25, that is 6.25. So moment due to UDL becomes 20 into 2.5, that is total force due to UDL, and it will be at centroid. So its distance from support A is 6.25 meter. And then due to Vb, that is reaction at support B, its movement will be Vb into 5, and that is anti-clockwise, so it is written as minus. So summation of this total must be equal to 0. So if we calculate with this equation, we will be getting reaction at B, that is Vb as 124.82 kilonewton. And then if we calculate with first equation, that is Va plus Vb is equal to 153.9. So that equation is written earlier with summation Fy equal to 0. Now if we substitute this in that equation, we will be getting Va. So that Va becomes 153.9 minus 124.82, and that gives 29.06 kilonewton. So that is vertical reaction at A. Now after finding the reactions at A, that was horizontal reaction at A was 60 kilonewton, and vertical at A is 29.06 kilonewton, and also we have calculated reaction at B, that is 124.84 kilonewton. So further it was asked that draw axial force diagram and shear force diagram and bending moment diagram. So initially we will start with how to go for calculations regarding axial forces at different positions and how to draw AFD, that is axial force diagram. So try to understand the portion A to D over here from support A up to point D, it is subjected to tensile axial force of 60 kN. So what we have at support A, the reaction is 60 kN is opposite to x-axis, and the horizontal component of this inclined force, that is 120 cos 60, that is 60 kN acting at D. So these two forces are in between A to D. It is acting at A and acting at D, and beyond D there is no axial force as such. Okay, so it is due to horizontal component of inclined 120 kN applied external force at D and the horizontal reaction component at support A. So due to these two external forces, part AD will be subjected to tensile stress or change in the length. However, the portion D to C will not be subjected to any axial force. So from D to C there is no axial force as such. So whatsoever change in length is taking place due to these two horizontal forces, that is horizontal reaction and horizontal component of applied external force. So due to that, change in length will be taking place in between A to D, and length D to B and B to C will be remaining as it is. So now the axial force diagram will be as shown in figure 11C. So let us say what we have. This is at A it is 60 kN, at D also it is 60 kN, and in between D to C there is no horizontal force, so there is no axial force acting over there, and that is axial force diagram now. And then in this axial force diagram, what is drawn over here at the bottom is, now A is original position of this point, and it will be as it is because you have some support system at that point. But the length AD will be getting increased, and the position of D will be somewhere as shown over here as D dash. Okay, and the length between D to B will be as it is from D dash to B dash, or length between B to C will be as it is from B dash to C dash. Okay, so change in length is taking place in between AD, and from D to C length is same as it is. So that is the axial force and the deflection taking place due to that axial force. Okay, so this is the discussion regarding axial forces and axial force diagram in case of beams. We will go further for shear force diagram. So here the deflected shape will be as shown in the figure. So we will go further with the shear force diagram and calculations for shear forces. So again we will be considering three different sections, say section 1-1 in between A to D, because at the left of section 1-1 as shown over here we have the reaction at A, but if we go beyond D, in between D to B, if you consider forces acting on left side, then you have a vertical reaction at A and a downward force, that is inclined force is there actually. Vertical component of that inclined force will be there, which is required to be considered in the analysis of shear forces. And beyond B, if we go further, then you have on the left side, in addition to earlier forces, this 124.84 reaction at B and 20 kN per meter, the uniformly distributed load in between B up to section 3.3. And or otherwise, because that equation will be much more equation. Okay, so instead of that, what we can do is we can consider section 3.3 and we can consider origin as C, and then we can consider the forces which are acting at the right part of section 3.3. So that will give us the calculations in a faster way. So if we consider section 1.1 and left forces acting on section 1.1, that is just this VA, that is reaction at A, vertical reaction, and that will be 29.06. So it is written as it is. HA is horizontal force. So that is not going to create any shear as such. So that will not be there in the equation. And now x term is not there related to shear force. So at point A, where x is equal to 0, then at that point shear force will be 29.06 kN. So also if we put the distance of point D, so that distance is 3 meter. So if we consider that point D and just left part of it, then again only this reaction is there, 29.06. So that shear force value will be 29.06 as it is. If we go further with section 2.2, considering in between D to B, and still if we say origin is A, so D is at 3 meter from A and B is at 5 meter from A. So limits becomes 3 to 5 meter if we are considering origin A. Okay, so and from section 2.2 position, the distance from support A is written as x2. Okay, so x2 is applicable in between from D to B or from limits 3 meter to 5 meter. So if we consider the section 2.2 and if we consider the forces at the left of that section 2.2, then the equation for SF22, shear force 2.2 will be, we have 29.06 kN vertical force and it is vertically upward, so it is positive, and we have 120 kN inclined force. Out of that, if we consider horizontal component and vertical component of that will be creating shear. Okay, it will try to cut vertically the cross section. So that is 103.9. Okay, that is 120 sin 60 is 103.9. So that is taken into equation. So this is giving us SF22 as minus 74.84 kN. So again x term is not there. So at D, if x is 3 meter, shear force is same as minus 74.84 kN, as well as at B, if we consider x2 as 5 meter from A, then shear force value is same, 74.84 kN. Now further, if we go through section 3.3, and now instead of considering the forces acting on left part, if we consider forces acting on right part of that section 3.3, and now if we consider origin C, then at C the distance x3 will become 0, and if we consider B, so that B, if we take this section at B, then x3 will become 2.5 meter. So if we are considering left part of section 3.3 with C as origin, then x3 will be 0 at C and 2.5 meter at B. So limits becomes 0 to 2.5, and we'll be considering the right part of that section, and we'll be writing equation for shear force at section 3.3. So then SF33 will be the UDL is there, 20 kN per meter acting on x3. So 20 into x3 is the total force due to UDL, and that is acting downward. Okay, but even if it is acting downward, it is written as positive. Now why it is written positive is, in sign convention we have discussed that if we are considering the left part of the section, then at the left part of the section the upward force is positive, and at the right part of the section downward force is positive. Or else, if we are considering a section and if we are considering left part of the section for the analysis, the forces on the left part which are downward are negative, and the forces towards the right part, if it is upward, that is considered as negative. So that was sign convention what we have discussed in earlier lecture. Now if we substitute the limits in this particular equation, then at point C, x3 is 0, then shear force at that particular position is 0, and if we substitute value of x3 as 2.5 meter at B, that is the upper limit. So if we put at point B x3 is equal to 2.5 meter, then the shear force becomes 50 kilonewton. Okay, so now the shear force diagram can be drawn, and that will be something like this. Now try to understand. In between A to D, there is no other force. So and if we go through equation of SF11, there is no x term as such. So power of x over here is 0. That is 1. So 29.06 is giving us the horizontal straight line or horizontal variation, or there is no variation in between A to D. The value of shear force is 29.06 kilonewton positive. Due to point load 103.9 kilonewton at D, then there is sudden decrease in the value of shear force, and that calculation gives us it is minus 74.84 kilonewton at D, and that is with this SF22 equation. So that is 74.84, and at B for here this is again 74.84. So there is horizontal line because in SF22 equation again x term is not there. But at B, due to reaction at B, that is 124.84, again there is sudden increase in the value of shear force, and at B with SF33 equation we got the value as 50 kilonewton, and at C, that is free end, the shear force value is 0. And now if we go through equations, in equation SF11 as well as in equation SF22, x term is not there. So the variation, if you want to draw, that will be horizontal line. However, in between B to C or C to B, whatsoever equation is written, x term is not there in the equation. That is SF33 is equal to 20x1, x3, and power of x over here is 1. So that will be inclined straight line between B to C. Okay. So with this we will go further for calculations of bending moment at different positions, and how to go for drawing bending moment diagram for given situation. So again we will go through section 1.1, section 2.2, section 3.3, and now we will be considering the forces acting at left of that particular section, and what will be bending moment of that particular force at that particular section. So say first we will be considering section 1.1 in between points A and D, and the distance x1 from A as whatsoever we have written earlier in case of shear forces also, with origin A, and the limits will be 0 to 3 meter, because whatsoever we are writing it for the position A to D, and that distance is 3 meter. So at A it becomes 0, at D it becomes 3 meter. So if we write the equation, the bending moment due to, because at the left of that section 1.1 there is only this reaction 29.06 reaction at A. So with this that bending moment of this reaction of 29.06 is at the distance x1 from section 1.1. So bending moment 1.1 will be 29.06 into x1, and now if we substitute those limits, at A x1 is 0 and at D x1 becomes 3 meter, and then if we calculate the bending moment, then it gives at point A as x1 is equal to 0, bending moment is 0, and at point D x1 is equal to 3 meter, hence the bending moment will be 87.18 kilonewton meter. So again if we go further and if we consider section 2.2 in between point D and point B. So if we are saying that from origin A its distance, that section 2.2, its distance is say x2, and it is if applicable in between D to B, then from A to D distance is 3 meter, and from A to B distance is 5 meter. So with origin as A for section 2.2, the limits will be 3 meter up to 5 meter. So if we go through that, and again if we consider the forces at the left part of section 2.2 for calculating bending moment values. So for first reaction over here, that is 29.06 VA, that bending moment due to that will be 29.06, and perpendicular distance between that force up to section 2.2 is written as x2. So here 29.06 into x2 is the first term, and second term is you have this 120 kilonewton inclined force. So if we consider the horizontal component of that, that is 120 into cos 60, that is 60 kilonewton, and it is passing through, it is horizontal, so there is no movement getting developed at B due to that horizontal component. However, if we consider vertical component of that inclined force, so that is 120 into sin 60, so that is 103.9, and now it is at D. So you try to understand from A up to section 22, distance is x2, and from A to D, the distance is 3 meter. So in between D up to section 22, distance will become x2 minus 3. So that will be the bending moment of this vertical component of this inclined force. So that will be 103.9 multiplied with x2 minus 3. So that is written in second term. And then if we put the limits at point B, if we substitute x2 is equal to 3 meter, then it gives us bending moment at that point as 87.18 kilonewton meter. And if we put the other limit, which is at point B, that x2 becomes 5 meter, then the bending moment value at that position is minus 62.5 kilonewton meter. So why it is minus, we will again discuss about it. So considering section 3.3 in between points B and C, so over here, now we are considering section 3.3 in between B to C, and now instead of considering origin towards left, we will be considering origin towards right. So C we are considering now as origin, and this section is applicable in between C to B. And if C is the origin, x3 is the distance from C up to section 3.3. And then if we consider right part of that section 3.3 and the forces acting on right part, we will be in position to find the bending moment at C as well as at B. So if we consider that force, that is 20 kilonewton per meter, that is uniformly distributed load. So point load due to that, or total force due to 20 kilonewton per meter uniformly distributed load, will be 20 into x3 from C up to section 3.3, and its centroid will be at x3 divided by 2 from section 3.3. So moment due to that will be whatever total force is multiplied with x3 divided by 2. So it gives us 20 into x3, that is total force due to UDL, and moment of that up to section 3.3 will become again x3 divided by 2. So it gives 20 into x3 divided by 2. So you can directly write it as it is minus 20 into x3 square divided by 2. And why it is written minus is, now if we consider the structure from position B up to position C, then due to UDL, C is free, so it will deflect down, and at B there is no vertical deflection as such because reaction is there. And then as C is deflecting down, then from B up to C, the deflection taking place is hugging type of deflection, and then there will be negative bending moment from C up to B, and from B onwards it may be up to some part, it may be again negative, and then further it will become sagging type of bending moment, or the value will be positive. So likewise, if we go through that diagram, before that we will calculate now what are the magnitudes of bending moment at C. So at C, x3 is 0, so that gives us bending moment at 3 and at 0. And at point B, x3 is equal to 2.5 meter, that gives us bending moment as minus 62.5 kilonewton meter. Now, the bending moment diagram will be as shown in this particular diagram. Okay, so try to understand. At A, the bending moment value is 0. At C, again bending moment value is 0. At B, over here, at support B, the bending moment value with BM22 equation is 62.5 minus and at bending moment 3 equation also the value is same, minus 62.5. So it is drawn downward and written over here is 62.5. And if you go through the equation written for section 3.3, that bending moment 3.3 equation, the power of x is 2. So here the variation in between B to C of bending moment will be a parabolic variation. Okay. However, in case of other sections from A to D, if you go through bending moment 1 equation, x term is there, but the power of x is 1. So here the variation from A to D of bending moment will be inclined straight line. So also in section 2.2, if you go through bending moment 2.2 equation, now in first term x2 term is there, in second term also x2 term is there, but the power of x in both terms is 1. So again from D to B, that is inclined straight line. So this gives us actual the bending moment diagram of the complete beam. Okay. Now try to understand, in earlier cases when it was a simply supported beam and the supports were at the ends, at the left end or at the right end, then at the left end and at the right end, in case of simply supported beam, the bending moment at that position will be 0. In case of overhanging beam, at the support where overhanging is not taking place, that kind of support will be subjected to 0 bending moment, or else we'll be having another part where the position is free, there is no support, as in this numerical at point C it is free end. So at that free end, in case of simply supported beam which is overhanging, the bending moment value will be 0. But in case of overhanging beam, the support through which the overhanging is taking place, say for this example that was support B, will be having some bending moment value over there. Okay, and generally that will be hugging type of bending moment, or that will be negative. With this, we'll go further for calculation of maximum positive or sagging bending moment is at point D. So that because the variation from A to D is a inclined line, and from D to B again it is inclined line, but at B it is negative, so it is coming down. Okay, so there is no other position where the bending moment value will be maximum. So maximum positive or sagging type of bending moment is at point D, and that is known, it is 87.18 kilonewton meter. It is not required to be calculated as such. And negative or hugging type of bending moment maximum is 0 at C, and at in between D to B, somewhere it is changing its nature from positive to negative. Okay, so at that position the value of bending moment is 0. So at B, whatever bending moment value is the maximum negative or hugging type of bending moment, and that is 62.5 kilonewton meter. So we need to go for calculation of point of contraflexure, okay, or where the nature of that bending moment is changing, either from hugging to sagging or sagging to hugging. So similarly, as a bending moment at point in between points D and B is changing its nature, so we need to go for a calculation of that. So what we'll be doing is equating equation of bending moment 2 to 0. So bending moment, the section 2 was in between D to B, and in between D to B, when we have drawn this diagram, somewhere at one position the magnitude of shear bending moment is changing its nature from positive to negative. Okay, so if we now equate that equation BM22 to 0, then we'll be in position to find the position at which that point of contraflexure is existing. So now BM22, this equation is already written, is equated to 0, and that if it is calculated for x2, it gives X is equal to 4.165 meter from point A, because for section 2 to origin was A, okay, and x2 was the distance from A up to section 2 to. So at x is equal to 4.165 meter from point A, the nature of bending moment is changing from sagging to hugging, which is point of contraflexure. This point is called as point of contraflexure. So with this discussion regarding numerical 10, we will conclude now this lecture. I am thankful to you all.